Hi everyone, welcome to a new video. Today I'll be covering uh, another DeFi challenge from the Damn Vulnerable DeFi series. This is actually the second challenge called the Naive Receiver. The challenge is basically another flash loan wherein you have a fixed fee and you have to drain the balance of the player who is trying to run the contract. Let's go through the code real quick to understand some of the concepts. There is a lot of concepts in this topic. Like each specific things is going into another 10 different things. So there's a lot of nuances here. We have a few files, that is the flash loan receiver, the naive receiver pool, the basic forwarder, the multi-call. The main logic is actually in the naive receiver pool file. So there is a multi-call and there is this IRS 3156 for the flash loan lending. But you can see if you go down, there's a fixed fee of 1 Ethereum present, which is very expensive actually. If you go down, first thing to know is there is a max flash loan which is actually checking the address of the token, the flash loan fee which we have, which is actually returning a fixed fee. Now core logic is actually in the flash loan. A flash loan is actually taking in the receiver address, a token amount and a random data or the call data, whatever is being sent, and it checks for if it's the actual currency or actual WETH that is being sent. It transfers it using the address of the receiver and the amount. It really doesn't actually do a foolproof check on if this call is actually legitimate. So that is kind of the problem that is here. So if you just send maybe 10 or 20 calls on this, it will just keep running this and it will keep reducing the fixed fee. Like even if the amount is zero, it will keep reducing the fixed fee from the person who is trying to run the flash loan. That is one of the issue here. As you can see amount with fee. So every time if you call it, the fixed fee will be added even if the amount is equal to zero. That is one of the issue here. And now if you go here, there is a withdraw function. Withdraw function actually calls the message sender here. And if you go into, okay, now this is a second issue that is there, that is this withdraw function. Withdraw function doesn't really have the problem, but the message sender actually uh, is another function which checks for the trusted forwarder. Now you might ask, what is a trusted forwarder? Think of a trusted forwarder as a pool that is whitelisted for the transaction. That is something this contract actually trusts. In order to understand more about what trusted forwarder is, you need to actually go to the basic forwarder. Basic forwarder is another implementation wherein it is actually taking in the request where there is this is structure of from the target value gas nonce data deadline. uh, so think of it like this. When you are actually trying to run this contract, the basic forwarder will take all of this information and use that and use that with trusted forwarder. Trusted forwarder actually checks that, hey, is this contract actually runnable in this thing and is it legitimate, and then it executes it. It's actually an implementation of EIP-712, a signing module, uh, a trusted signing module that is present. There isn't much specifically here that we need to look at, and there is an execute here which we will be calling in order to finally get the money out or get the Ethereum out. Okay, now in execute function you can see some specific things like there is an assembly and there is an encoded pact. So there are two types of encode pact here. Like there is, you can just use ABI encode and ABI encode pact. ABI encode pact has two parameters like the data and the request from who is sending it. And this is very important actually because you will be using it later. I'll be explaining it further. Um, you can use encode. Encode will send in the entire data, but packed will actually really pack it without any padding or anything. And we are using some assembly, or the contract is actually using some assembly. You can see a payload, add payload of, and they are giving a hex value of 20. So the meaning here is that in order to actually identify the length of the contract or the details of the contract, you actually, or if you have multiple arrays, you actually need to know what size is the array. So that is actually in the first 20 bytes. So once you take the payload, and this mload is actually reading what is the size of the array. Uh, okay, this is, now you might ask, where is this array coming from? Um, then there is something called multi-call. Say if you want to do 10 or 20 or 100 transactions in one go, you can use multi-call to sign a lot of things before the contract executes, which stacks it up, and it gets executed in one single super call. So see, these are a lot of concepts, and 0 0 doesn't mean we are not taking any input or any standard out or anything like that. Then there is a gas left with request gas divided by 63. So this is a cool concept that came in 2016. So that means we should have uh, in every transaction the total amount of gas is split into 64 parts, and any transaction can use 63 of the available 64 parts. The last one is present so that whatever happens, the contract gets completed. So it's kind of a fail safe that is present, and that's enough information here. So I covered a lot of information here. So the aim is to actually okay, now I didn't come to why this message under an issue. So say if you got the private key of a person, and if you're able to sign a signature with that and send it to the trusted forwarder, the trusted forwarder will actually think it is a genuine contract, and it will send it along. And and when you call the withdraw function, it will actually call this message sender, which will actually take in that player's signature, and you can actually take the amount from their account and put into your account. That means the fees that you deducted from the user can be deducted, can be moved to your account using this withdraw call. So that is basically the vulnerability here. So I have already wrote down the exploit. So I'll explain the test file that is present here to give you more context. So there is 1,000 Ethereum in the pool, and the receiver has 10. So we are trying to reduce 10 from the receiver, that is from the player. We are actually starting the virtual machine with player, and while setting up UV, there is something called player key PK, which is actually the player's private key, because we need the private key of the player to actually sign the contract. In the real world this won't work. You need actually a, if you're attacking the person or something, or some, you need to actually have that person's private key. So this is just a CTF challenge at the moment, so we are actually having the player's private key. And if you go, the basic forward is being defined, and these are all basics. And if you go down, this is asserting the initial state, which is not very important, but uh, the check for the solver, there's a solving check that is, or the solver check that is present. If you check the solver check, they are asserting that, the transaction gets executed in less than 2 transactions. That is the reason why we will need the multi-core and something called a meta transaction as well. Straightforward, that is actually the meta transaction here. So that is it, and you can see the weight plus in pool plus weight receiver. That is what they are checking for. So we need to actually reduce the entire money in the player's account and put it in here. Now we have the context. Now we are actually going into the function. This is actually, there's nothing here. Now this is how the exploit looks like. So since we need to see, at every transaction you can take 1 Ethereum from the player's account. So we need to do a loop of 10 times so that it calls it 10 times so that we can reduce 10 Ethereums. So that's why we have an array declared of size 11. I'll tell you why we are declaring of size 11, because here we are looping through 10 times. We are calling the flashloan function. We have the receiver address. We have the address. We have 0, and this is an empty address. You can put anything here in this case. So now you basically have 10 elements or 10 array 10 iterations of calling flashloan. Now if you go down, as I mentioned, total funds is equal to what's in the pool with plus what's in the receiver. Receiver has 10 Ethereum. We need to reduce that. So that is what we are seeing. That's what we are putting in total funds, because that needs to be checked. Last position of the array, we are actually putting an encode pact, which calls an encode code. Okay, in ABA encode pact has, so we will have the request.data and from. So this ABA encode call will contain the data, and this will actually contain who is it actually from. So it's actually from the deployer. And you might ask, why are we doing this weird bytes 30 to UIN 256 and UIN 160? So you actually want the deployer's address to go as a 32 bytes, because the reason being Ethereum supports everything in 32 bytes here. So when you send this into the ABA encode pack, the request.from should actually be of size 32 bytes. And okay, again, this will be only of size 20 bytes, the deployer. The rest 12 bytes will be a padding of zeros. So it will only take the last 20 bytes. So that is what is happening. So we are actually padding extra 10, 12 bytes into this. All the ABA encode pack request.from is actually taking 20 bytes. Or okay, so now we are actually calling the withdraw function finally with all of these information. Okay, so now the array is filled. Like first 10 is calling flash loans, and last one is actually the withdraw call. So now we have everything. Now we need to actually make it into the batch call, that is the multi-call. So that is what we are doing here. We are creating a multi-call data and encoding all of it. We are calling the pool.multicall with the entire array being given here. So that actually makes multi-call data contain all of the call datas, or like 10 flash loan calls and one withdraw call. Finally, we need to create a meta transaction. Think of meta transaction as the trusted forwarder transaction that we want to do. It does all of it off the chain, and finally we can bring it all together into one super call. So that is basically happen here. So basic forwarders request, as we have seen, the structure we are again defining it here. The player, the address pool, value is 0, and the maximum gas value that we can give, the nouns of the player, the multi-call data, and the timestamp. So we are actually creating a request. Now we need to actually sign this request using the player's private key. As I mentioned, this is very important, so that trusted forwarder actually, uh, when trusted forwarder is being checked with this with basic forwarder request, it understands that, hey, this is actually signed by the player's private key. If you think about it, it's actually using ECDSA, like, so you will have the XY curves and all of that. I'll come that in a bit. We are using again ABA encoded pact, and we have a hash as well. These are the magic bytes. I think these are required for EIP-150 to make sure that that hash is also following the Ethereum thing, and we have a domain separator and the get hash request. Finally, we have a VM sign, which is actually using the player's private key and the request hash that we just created. So the first one is actually the public key value, which will be like 27 or 20. There will be two values two public key values that can be there. So this is actually telling which one to choose from. The first one will be the x coordinate and the second one will be the y coordinate, because it's actually in a curve. So ECDSA, right? So elliptic curve. So you will have an x-axis value and a y-axis value in 32 bytes. You are storing that again as a pact in signature, so that if you use your public key to check it, yeah, public key of the signer to check it, you can understand that hey, this is a valid signature. Now we finally execute it using the request that we have generated from here and the signature. This will actually complete the transaction. There's a lot of nuances here. I think you will have to probably read out on more of the things, but if we just test it, it works perfectly and everything is successful. So this is the native receiver challenge in Damn Vulnerable DeFi. It's a complicated challenge, but it actually teaches you a lot of nuanced details. Thank you all so much for watching. I'll be back next week with another video.